Quantum Foam. Episode 24. Maxwell's Equations.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely that's not going to happen, but
Forces which govern the universe. Physics.
James Clerk Maxwell. All right. I'm thinking that before we get too far into some of this stuff here, it would probably be good to go over a primer on a few other individuals before we really get into electromagnetism as opposed to Maxwell's electromagnetism, because it had some roots before he came around. He's famed with having the derivation and doing it the correct way. But let's go into André-Marie Ampère, amps. He was a French physicist and mathematician. They consider him a founder of the science of classical electromagnetism. He referred to them as electrodynamics, but he's got a circuital law, force law, right-hand grip rule, and some other stuff here. But he is important because Ampere's circuital law is something to note. There's a different law, Ampere's force law. That's the force of attraction or repulsion between two current-carrying wires. That can be called Ampere's force law, but this is the circuital law. It relates the integrated magnetic field around a closed loop. So Maxwell actually derived it using hydrodynamics, using actual experiment. But of course, it's one of Maxwell's equations now. Important. We also have Michael Faraday. He was English. He didn't even have any formal training, really. Scientist. He contributed to electromagnetism and electrochemistry. Didn't even have any formal training. His main thing is electromagnetic induction. Scientist. The production of an electromotive force across an electrical conductor in a changing magnetic field. Didn't even have any formal training. He was a really good experimentalist, so he's finding out a lot of things.
I always thought what Michael Faraday did was pretty awesome. No formal training. Most people need school, college, military training, or higher learning of some kind in order to aspire to a professional level, such as a doctorate in a subject. But when you are on the forefront of science, sometimes there is no previous teacher who knows how it all works, and so is able to teach the younger generations.
Due to one thing or another, he's getting high positions. He got appointed to a position in the Royal Society. This is obviously a person Einstein thought was important.
That much is true. Michael Faraday started the modern understanding of magnetism, and began fusing it together with Sir Isaac Newton's calculus formalism. For I have once declared, and once again shall I declare, that I have stood upon the shoulders of James Clerk Maxwell, who, presumably, had stood upon the shoulders of giants, as the saying goes.
Along with Isaac Newton and James Clerk Maxwell, of course. Some of the stuff that Faraday did, these are in the 1800s, a little bit before
Isaac Newton's calculus formalism.
James Clerk Maxwell. So Faraday was mainly a chemist. He's best known for his work regarding electricity and magnetism. So he's doing lab work in the 1820s here. Diamagnetism. A few other things here. Later on, we're going to get into the equations a little bit, but I thought that we would also do a miniature primer on some of the mathematics that might be required to understand what it is we're even talking about here. Vector algebra. All right, 3D grid, XYZ stuff. Unit vectors, I, J, K, I hat, J hat, K hats. So when we're splitting up a component of a vector, epic. In 2D, you have one component on the X parallel to the X axis, one component parallel to the Y axis, and that is the Y component and the X component. Epic. And so this vector randomly goes at a, let's say, 30-degree angle. This is a 2D grid. So there is a component of the X and there is a component of the Y, and they can be found out with cosines and sines. And depending on where you place them in the grid, if you're in the positive, you're using positive. It gets a little bit bit confusing when we're using these unit vectors, x hat, y hat, z hat. Epic. But we need to understand these. So here's an example. Vector A is equal to a sub x, x hat, plus a sub y, y hat, plus a sub z, z hat. So x, y, z hats are the unit vectors. And so the a sub x, x hat, and the a sub y, y hat, and the a sub z, z hat, those are the x, y, and z components of the vector A. Epic. The vector A can be written as A with an arrow over it. And so the difference is A sub x, A sub y, and A sub z are the magnitudes of vector components. They are the magnitudes of these vector components. That is different than describing what the unit vectors are, and also what the components of the vectors are, what the components of vector A happen to be. Epic.
This stuff can get really dry, man, but I know we need to know it. Understanding vectors and making sure that we don't mess up magnitudes or directions is diabolically crucial when producing good physics equations.
So that is the difference between the components. You got the different additions, you add them up, you get an answer. Using angles, you're doing things like magnitude of vector A times magnitude of vector B times cosine of theta, an angle. That is equal to the dot product of vector A dot vector B.
I think I can help out here a little bit. This operation is done simply by breaking up the x and y components of the vector to see what forces are applied to what. Cosines and sines have to be used to represent how much of the angle counts toward the force in that particular direction. Let's say we want to know how much force to move a box that is modeled along the y-axis. If we pull a string that is attached to the box in the middle of one of the sides and pull at a downward angle, we are only applying a partial vertical force along the y-axis. To calculate how much force is acting in the vertical direction, we take the cosine of the adjacent angle that is superimposed next to the string that adjoins the box.
It looks like you guys got it. The math checks out on my end.
We are looking at the picture from the side and only care about 2 dimensions.
What if it is referring to the opposite?
We would use a sine if we were interested in the opposite angle.
The standard dot product.
So by Cartesian components, the dot product of vector A dot vector B is equal to A sub x, B sub x, plus A sub y, B sub y, plus A sub z, B sub z.
I think they're getting it.
And so it's not exactly the same thing as times. The dot product represents the projection of A onto the direction of B multiplied by the length of B. So it gives you sort of your x side of your triangle. So the scalar product can be particularly useful when one of the vectors in the product is a unit vector. That's because the length of this unit vector is always 1. So the scalar product, such as the vector A dot z hat, finds the projection of A onto the direction of z hat, which is the z direction.
Yes, the unit vectors can show you which direction to place your grid.
To find the component of any vector in any given direction, you can simply form the dot product between the vector and the unit vector in the desired direction.
Not bad.
In physics engineering problems, you frequently encounter the need to know the component of vector A that's perpendicular to a specified surface. If you know the unit normal vector in hat, the scalar product vector A dot in hat gives you that particular component of A. The scalar product can be used to find the angle between 2 vectors. The derivation is this. Vector A dot vector B is equal to the magnitude vector A times magnitude vector B cosine theta is equal to A sub x, B sub x, plus A sub y, B sub y, plus A sub z, B sub z. So the cosine of theta is A sub x, B sub x, plus A sub y, B sub y, plus A sub z, B sub z, all over the magnitude of vector A times the magnitude of vector B. Further reducing to find out what the angle is. The angle is equal to the arccosine, inverse cosine, cos -1. The angle theta is equal to the arccosine of A sub x, B sub x, plus A sub y, B sub y, plus A sub z, B sub z, all over square root of A sub x squared plus A sub y squared plus A sub z squared times square root of B sub x squared plus B sub y squared plus B sub z squared.
If they want to follow along, I would pause the podcast and get a pen and paper.
Complicated, huh?
It surely can get that way sometimes.
Not really. If you had it on a piece of paper, you could see it.
Pen and paper it is.
So the dot product between two perpendicular vectors gives a result of 0 when the degrees is 90 degrees. Cosine theta is equal to 0. This feature is frequently used to determine whether two vectors are perpendicular to each other or not.
We get the dot product, go into the cross product. That one is a little harder to comprehend.
Alright, this cross product, or the vector product, it's the cross product. When you see that cross sign, we say cross, this is what we mean. The cross product between two vectors results in another vector. This is very useful in physics, such as when you are trying to find the result of applying a force at the end of a lever arm, or firing a charged particle or something into a magnetic field. The cross product of two vectors A and B, denoted A cross B, is a vector perpendicular to the plane that contains A and B. This magnitude is magnitude A times magnitude B sine theta, where theta is the smaller angle between A and B, and its direction follows that the right-hand rule when the fingers rotate from A to B through to angle theta. So this can be looked at like an important difference between the dot product and cross product is that the order of the vectors is irrelevant for the dot product, but it matters greatly for the cross product. So obviously, if it's A cross B, that A needs to be first. It's not the same as B cross A. Cross product is not commutative. It can exchange positions. If you know the Cartesian components of both vectors, the cross product is given by.
Okay, I actually have a pen and paper this time.
Vector A cross vector B equals, we got a grid system here, x hat, y hat, z hat. Under the x hat, we have A sub x and B sub x. Under the y hat, we have A sub y, B sub y. Under the z hat, we have A sub z, B sub z. So this is actually equal to A sub y, B sub z minus A sub z, B sub y, all times x hat, plus A sub z, B sub x minus A sub x, B sub z, all times y hat, plus A sub x, B sub y minus A sub y, B sub x, all times z hat.
I can't tell if I'm faster at writing or typing.
Using the definition of the cross product and in conjunction with this right-hand rule, you can see that these relations are true. They might help you.
Writing it down for future reference.
I hat cross I hat equals 0, J hat cross J hat equals 0, K hat cross K hat equals 0. Source code. I hat cross J hat equals K hat. Source code. J hat cross K hat equals I hat. Source code. K hat cross I hat equals J hat. Source code. J hat cross I hat equals negative K hat. Source code. K hat cross J hat equals negative I hat. Source code. I hat cross K hat equals negative J hat. That it just gives you a table just in case you need to use them. So if the angle between A and B is 0 or 180 degrees, which means A and B are parallel, the cross product between them is 0. This feature is frequently used to determine whether two vectors are parallel or not. Cross product is also used for torque problems and magnetic force problems. That is what we are getting into here. Magnetic force problems. Maxwell's equations. That is why it's very important that you understand what the fuck the cross product and the dot product are. We could get into some examples of these, but we'll say that we can do those on our own because we're getting into a little bit higher level material here and we can study the math on our own time. A few things might also need to be noted. The nabla is a triangular symbol resembling an inverted Greek delta. So this is like a triangle with two of the sides up top and the point on the bottom. So it looks like a pizza that you're about to eat. The name comes by reason of the symbol shape from Hellenistic Greek blah blah blah. That's the etymology. What's important about this is it denotes the three-dimensional gradient operator. Remember, in vector calculus, the gradient of a scalar value of a differentiable function, f of several variables, is the vector field, or more simply put, a vector-valued function, delta f, and I mean delta, this nabla, whose value at point P is the vector whose components are the partial differentials of f at P. So this is telling you there's math equations that go with gradients. The nabla, the del, usually represented by the nabla symbol. It denotes the standard derivative as defined in calculus. The del dot denotes the divergence operator. The del cross denotes the curl operator.
Got it. Well, actually, let's just do the midpoint real quick while I finish writing this stuff down.
Obviously, this is the midpoint of episode 24, Maxwell's equations of quantum foam. Now, a curl is a vector operator that describes the infinitesimal rotation of a vector field in three-dimensional Euclidean space. At every point in the field, the curl of that point is represented by a vector. The attributes of this vector characterize the rotation at that point.
Hold on, I have a question. So you guys have to add all this curl math to my calculus formalism?
Don't worry about it, Newton. Let us theoretical physicists of the 20th and 21st century handle this curl math stuff. You need computers to really work with the stuff, anyhow.
And I thought I had it bad.
I did plenty fine on pen and paper along with Kaluza, Klein, Dirac, Schrödinger, Heisenberg, Niels Bohr, and even fucking Boltzmann, as has apparently evolved into some sort of inside joke regarding Mr. Boltzmann. Whatever, I guess.
The curl. Now, a curl is a vector operator that describes the infinitesimal rotation of a vector field in three-dimensional Euclidean space. The curl. So this is in the curl. Differential equations, we're going to be using this, the curl, to figure out gradients, the curl, and such. This del, we'll call it del, because it's like delta, but it's nabla. So, the three-dimensional gradient operator, del. What's the del dot of this? What's the divergence operator of that? What's the del cross of that? The curl operator of that. And there's other uses of this and stuff too. The curl. Faraday's law, Maxwell's equations is what we're getting into here. So these equations can be formulated with time-dependent surfaces and volumes by using the differential version and using Gauss and Stokes formula appropriately. There's the surface integral we're doing over boundaries. We're doing a volume integral over a volume. We could do a line integral around the boundary of curves. We can do surface integrals, again, over different surfaces. And we can describe electric charge, physical property, and how that's enclosed in omega, and it's the volume integral. We also can have a charge density, P, rho.
Music to my ears. I'm sure it's the same with Sir Newton and Dr. Hawking, yes?
Yeah.
You know it.
There's important things here. Gauss's law for magnetism, Maxwell-Faraday equations, which is his law of induction, and then Ampere's circuital law with Maxwell's addition, which is the displacement current. This is pretty deep stuff, but it is somewhat of a primer on vector algebra before we get into a lot more sophisticated problems. So real quick, what we're really interested in here is doing these surface integrals. It's the area integral of a scalar function or vector field over a specified surface. It's best understood by looking at a practical problem here. Real quick, the area density of this surface varies with x and y. Real quick, we need to find the total mass of the surface. Real quick, we can divide the surface into two-dimensional segments, over each of which the area is density delta xy. Real quick, it's approximately constant. For each segment, the density delta, the area is dA. Real quick, and the mass, real quick, for the small segment is delta dA. The total mass will be the sum of the mass of all segments. The total mass is equal to sigma of n, I equals 1, of delta I dA sub I. Real quick, solution. Per calculus, when we make the dA, derivative of A approach 0, and the number of segments n approach infinity, this sum becomes the surface of integration. Per calculus, this is the area integral of the scalar function delta xy over the surface S. Per calculus, it is simply a way of adding up the contributions of little pieces of a function, the density, in this case, to find a total quantity. Per calculus. So we're going to be doing a lot of these to find so-called energy densities, dealing with flux, magnetic flux, per calculus, electric flux, lots of different flux things with that. Flux. And so, flux. James Clerk Maxwell. Let's get into this here. Who was this guy? He is the father of mechanical engineering as a profession. He built upon the equations of Michael Faraday. He is one of the best known figures in physics and math since Isaac Newton.
Sure, Maxwell was my contemporary back in the 19th century. Who knows? Anything is possible with an adequate understanding of my mathematics and physics.
He was highly praised by Einstein. It was said that Einstein said he stood upon the shoulders of Maxwell instead of upon the shoulders of giants?
Yes, indeed.
Well, I am standing upon the shoulders of Einstein and Stephen Hawking.
LOL.
But what is the importance of this guy? What did he do? It could be said that as far as making major contributions to natural philosophy or physics or science as we know it today, the first of which was Isaac Newton and describing gravity, the relationship between what gravity was mathematically. The second great revolution, combining magnetic phenomena and electricity, electric and magnetic phenomena, into electromagnetism. Why is this important? What is this? How did they do this? What is this? And so we can get into this here.
It might be a good idea to give some biographical info on Mr. Maxwell.
But to go into him a little bit, he was from Edinburgh, Scotland, 1831. What is this? He died at a young age of 48 in 1879 at the end of putting together the manuscripts of Henry Cavendish. He discovered hydrogen. Cambridge stuff later in life, but early in life, he was putting together papers at 14 and putting other papers together a little later on. They had to be presented by his tutor because they figured he was too young to be producing papers like this. But let's move to further. When he was old enough, easily rose to the ranks at each college, Edinburgh, then Cambridge, got various positions. He had particular interest in the rings of Saturn. He proved that the rings of Saturn were made of numerous small particles. Had to have been. There's that famous picture of James and Catherine Maxwell from 1869. They got a little pooch there. And it's funny because this is a drawing, likely. Maybe it's a picture. Probably a drawing. But he was the one who created the first color picture. He helped in the science relating to that, so that's pretty sweet. If you think about it, light is a picture, so that's pretty badass. Let's get a little bit more into some stuff here. What did his contributions really do? His big paper was done in 1873. It was treatise on electricity and magnetism. Essentially his 4 laws or equations, sections in fully developed form. It demonstrated the partial differential equations that demonstrated the commutability between electricity and magnetism in terms of mathematical flux. So, in a way, it really is leading towards laying the groundwork for relativity. He had helped people build bridges. People were starting to build bigger bridges. There were carriages, pathways, things like that were developing around more developed regions. They needed bridges built. He knew how to do it because damn near a mechanical engineer. Of course he knows how to do it. In his day, the problem was these forces by Faraday, the induced forces of magnetism. What is going on here? They're the same thing, equal and opposite of flux. What are these equations? They have to do with the permeability of an electromagnetic wave going through a material over a surface area or throughout a distance. So what was going on here? What is the importance of these equations here? They are sets of partial differential equations that contain many, many variable functions, unknown and enough to know their partial derivatives. So they're using these to solve problems, make problems, to describe problems, and so computer models and such are used to solve these. And then together with the Lorentz force, that's the combination of the electric and magnetic force on a point charge due to electromagnetic fields, a particle of charge Q moving with velocity v, and an electric field E, and magnetic field B experiences a force of F equals QE plus QV cross B. So, cross product. They form the foundation of classical electromagnetism, electromagnetic laws.
He was the father of many things, but all that is up for discussion.
Father of what is it?
Another good question is, did he actually get a PhD?
What did they say?
They really didn't have those in America until after he got his additional degree beyond undergraduate.
Father of mechanical engineering, electrical engineering. So this is very important. This is essentially the radio wave. This is your creating an antenna to pulse a radio wave using electricity and magnetism. The electromagnetic spectrum, the frequency of an electromagnetic wave. The wave peaks per second. You got the wavelength and the amplitude. So they're all the speed of light. The speed of light equals the frequency cross product, the wavelength, cross the wavelength. So F cross lambda equals C. C equals F cross lambda. So what this is giving us is the energy density of both fields, and they equal each other. Differential equations are this. You got part of the variables on this side, part of the variables on this side. You put in all the variables you know on this side, you substitute everything you can do, and one thing we know, according to these laws, is that the energy density of the electromagnetic field is the same as the energy density of the electric field, as well as the same as the energy density of the magnetic field. So it's all the electromagnetic field. It's all the same, 1 to 1 to 1. Knowing that, we can fill in a bunch of these variables and figure it out. Radio waves, all light, all forms of radiation. And so, first one, electromagnetic flux. It's the integral of the surface area. Second law, it's the same as Gauss's law, but this is with magnetism instead of electricity. Third law, same as Faraday's, but for flux. And it's also what gives us the difference between the magnetic flux and the magnetic field. What is a displacement current? We will need to know that for the entire equation. So this is relating the magnetic field and the electric field. You can use Ampere's law, the current, and the displacement current. They're putting these into these equations to figure out energy densities at any point in the propagation of a wave. So knowing all this stuff, you can create radios, you can create pictures, you can do a lot of different stuff. The velocity is 1 over the square root of E naught mu naught, the permeability of the electric field and the permeability of the magnetic field. The magnetic field is perpendicular to the electric field, hence the cross product. So a lot of this was important. So he did other things like solidifying gas and friction. Science in 1866, early on, the Maxwell distribution. The gas velocity at any given temperature is what it gives you. They'd explained these results better than what had been done before in thermodynamics. What he's doing is creating mathematical extensions of Michael Faraday's equations of magnetism, magnetic lines of force, putting them together. By the end here, he's putting together the papers of Henry Cavendish, editing and publishing them. That's the last thing he did in 1879. And that was the year Einstein was born. So very important shit. And there are a lot of parallels with things like this. Stephen Hawking's now no longer alive. And who else do you got? Who else is there? We're right here. But Maxwell's equations, for many different areas, they are part of this very elusive theory of everything. So this is an attempt to put together everything into one coherent formula. We're right here. Explained to the point to where people can understand it. There were contributions all over the board. This is 2 of the 4 main forces combined into one. So using these, Einstein better described gravity than Newton, having known stuff that was discovered by Faraday and Maxwell, and so quantum mechanics is in there as well.
Of course, you could say that Faraday and Maxwell were the scientific figures who had bridged the gap between Newton and myself over almost 300 years.
I first published my book on calculus, Principia, in 1687. He released his general theory in 1915. And here it is at last. The candidate for the elusive theory of everything is now being presented.
There are quantum consequences. This is the groundwork for both relativity and quantum mechanics in that order. We have already went over a brief primer on both quantum mechanics and relativity. We will be going through them again and again and again until we pick out what we need for the formula. This is it for now, and this is all we have on episode 24, Maxwell's equations of quantum foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Phone is produced by Zeroth Wave Productions.